Welcome back to The Explainer. If you've ever looked at a perfectly molded plastic part and wondered exactly how engineers guarantee it comes out of the mold flawlessly every single time, well, you are in the right place. Today, we're cracking open the engineer's blueprint for injection molding calculations. Now, I totally get it. At first glance, mold design math can seem incredibly intimidating. It looks like a chaotic jumble of formulas and constants. But don't sweat it, we are going to conquer this together. By the end of this explainer, you'll see the elegant, practical logic behind all these numbers. So here is our agenda for today. First, the ejection force challenge. Second, support pillar analysis. And third, perfecting gate design. Let's get right to work. Section 1. The ejection force challenge. Getting the part out without a hitch. Okay, so designing a mold is one thing, but getting the molded plastic to actually come off the core without breaking, warping, or sticking, that is a completely different beast. And that challenge requires the fundamental ejection force formula, straight from our source material. Now, I know what you're thinking. Look at that thing. It's a terrifying equation. You've got Poisson's ratio, thermal contraction, thicknesses, diameters. It honestly looks like something out of advanced astrophysics, but I promise you it is not as scary as it looks. We're going to isolate the most important variables right now and make perfect sense of it. All right, let's dive into this. Out of that giant equation, these are the absolute core physical variables driving the math. P is your ultimate goal, right? That's the total ejection force required, measured in kilograms force. E is the elastic modulus of your material. A is the total area of contact between your molding and the mold faces, specifically in the line of draw. And mu, that little Greek letter, well, that's the coefficient of friction between the plastic and the steel. What's really fascinating here is just how much the material itself dictates the required force. Take a look at this data from Table 5. If you're molding ABS, your coefficient of friction is 0.5, but if you switch your material to acetal, it drops exactly in half to 0.25. This brilliantly illustrates that acetal requires significantly less force to eject than ABS, simply based on how the material inherently slides against steel. Basically, you change the plastic, you completely change the math. Moving on to Section 2, support pillar analysis, keeping the mold intact under pressure. So let's see how all this builds into the structural integrity of the equipment itself. Before we get into the heavy structural stress math, there's actually a fantastic, rough rule of thumb in the source material for the ejector pin themselves. You always want to provide 1 square centimeter of ejector pin bearing surface for every 100 square centimeters of sidewall contact. Note that sidewall contact, not projected area. That is your golden ratio for pin placement, well before you even start looking at the larger support plates. Now, for the plate itself. Picture this. When you inject molten plastic at ultra-high pressures, the mold literally wants to bend and bow. We use support pillars to stop that from happening. Notice the 3 interconnected equations here for W, Z, and A. They calculate the permissible load, the section modulus of the plate, and the permissible projected area. At a glance, they might look separate, but they're actually a single connected chain of logic. Let's walk through that calculation chronologically, just like a master blueprint. Step 1. You find your permissible load, or W. Step 2, you calculate the section modulus, Z, which is based on the length and thickness of your support plate. Step 3, you determine your permissible projected area, A. To do this, the math gives us a standard working stress to plug in, which is 840 kilograms per square centimeter, and a maximum unit pressure on the support plate of 630. If you follow these 3 specific steps, the math tells you exactly how much area your current setup can safely handle. But wait. What happens if you run that calculation and your permissible projected area is actually less than your actual area? Well, this is crucial. If you have a deficit, you absolutely must strategically add support pillars. And the source material reveals an amazing shortcut here. Check this out. If you place just 1 row of additional support pillars equally dividing the span in the ejector grid, you don't just double your capacity, you literally quadruple the permissible projected area. It is a massive structural gain from a relatively simple design addition. All right, Section 3, perfecting gate design, getting the plastic in efficiently. So we know how to hold the mold together, and we know how to push the part out, but how do we actually get the plastic in there efficiently? Well, the gate is essentially your master control valve. The cross-sectional area of the gate controls the exact rate of fill into the impression. But specifically, I want you to consider the depth. The depth of the gate dictates the time for which the gate remains open. Think about it. If it freezes too fast, the extremities of your part just won't fill. But if it stays open too long, you're just wasting valuable cycle time. And this brilliantly illustrates the delicate balancing act engineers play every day. On one hand, the depth formula, H equals N times T, controls time. On the other hand, the width formula, W equals N times the square root of A divided by 30, controls the flow rate, or the volume. Basically, depth ensures the far edges of the mold get packed properly, while width dictates how fast you can shove the overall volume of plastic into the cavity. Let's ground this with a real-world number to make it concrete. See that N variable in both of those formulas? That's a material constant. So if you're molding polyethylene or polystyrene, you simply plug 0.6 into that N variable. Instantly, the formula sizes the gate perfectly for the unique flow characteristics of those specific plastics. Now, if you switch to polyacetal or polypropylene, you just bump that number up to 0.7. See? The math seamlessly adjusts to the material. Here is that final width formula in all its glory from the source text. And alongside it is a really crucial drafting guideline you've got to remember. The land length of the gate should be approximately equal to the gate diameter or the gate depth. It's exactly these precise combinations of width, depth, and land length that guarantee the molten plastic flows exactly how and when you want it to. Finally, the engineer's final checklist. Wow, okay, we have covered a tremendous amount of ground today. So let's bring all three of these critical mathematical checks together into one cohesive summary, your master blueprint. First, always check your friction coefficients to ensure your ejection force won't just destroy the part on the way out. Second, run your stress calculations to verify your pillar span and fix any area deficits, so the mold doesn't cave in under pressure. And third, calculate your precise skate depth and width using your specific material constant to optimize that fill time. Mastering these specific engineering variables is exactly what prevents catastrophic manufacturing failures down on the shop floor. I want to leave you with a provocative thought to ponder. Remember, these formulas, they don't exist in a vacuum. Let's say you decide to widen your gate to fill the mold faster. While doing that, might alter the internal pressures. So will your support pillars still withstand that new dynamic? It's a great reminder that injection molding is one single, highly interconnected system. Change just one variable, and the whole blueprint shifts. Thank you so much for joining me on this explainer. Keep asking those tough engineering questions, and I'll catch you next time.